Okay, so in the previous lecture we had introduced the notion of metrization of a given topological vector space, and in this lecture we would talk about or rather we will start talking about boundedness and continuity. Okay, and why is it essential to talk about boundedness after we have introduced the notion of metrization? It's typically the fact that we have one sort of a definition of boundedness already in hand related to the notion of a topological vector space. So let us just quickly recall that definition. That so we are assuming X to be a topological vector space. I'm not writing that out again. So E in X is bounded, and what was our usual sense of saying it to be bounded? If we have if it is contained inside scaled neighborhoods for sufficiently large scale, right? So E is bounded if for all neighborhoods V of the origin in X to be precise, there exists some S greater than 0 such that E is contained in TV for all T greater than S, right? Or the other way of saying it is that E is completely contained in this in these sets TV for sufficiently large T. So this is our usual definition. This we will be treating as our usual definition. Our usual definition of boundedness. But if you have studied metric spaces precisely, then we have some notion of boundedness with respect to the metric as well, right? So this is what we call the definition of metric boundedness, or rather which we will be denoting as D boundedness, but D will be referred to the metric we will be working with. So how is it typically defined? So if D is a metric on some space X, then E in X is said to be D bounded, that is bounded in terms of the metric, if there exists some finite number m such that the distance between every point in E is less than m. So this is less than m for all xy in E, right? Yeah. So if I talk about a simple diagrammatic representation of what both of these mean specifically, so yeah, so suppose I have suppose this is my topological vector space, let's say X, and I have some set, let's say here E. Now diagrammatically they will somewhat seem to be same, because when we are drawing out things, when we are picturing picturizing them out, it's in some sense Euclidean, right? So we have a norm on it, and the metric which is keeping on which keeps on going in the back of our mind is also the usual metric. So it will seemingly be the same, but rigorously they need not be same. We will come to that later. But if this is E, then we say that it's bounded if we start with some neighborhood from the origin, and there exists a neighborhood sufficiently large so that if I keep on making it further large, E will still be contained inside. So this is from the usual definition what we call the TV in some sense. And if I talk about our notion of the D bounded, so if I choose any 2 points from inside, suppose I choose 2 points from inside, any 2 points from inside, then the distance between them, the distance dxy between them, this should always be less than some positive number. Okay, this should always be less than some positive number. Fine, some fixed positive number to be more precise. Fine. Okay. Now, as I remarked that deboundedness in general need not be equivalent in terms of definition, equivalent in terms of concept to usual boundedness, but for obvious reasons we are omitting out the specific example because we have not discussed the proof of the metrization. The proof is a bit complicated to talk about in some sense, but we will still try to give a proof of it later. I am not going to indulge into that at this point, but once we have the the proof of the metrization, it actually in that proof we construct out a metric specifically, and when we are constructing out that metric, that specific metric will serve as an example to this remark. Okay, but so since we are omitting out that proof for now, we are omitting out this example as well for now, but you need to keep in mind that deboundedness is not in general equivalent to the usual topological vector space boundedness. Okay, and this is even if D is invariant, even if D is invariant. Fine. Okay. Yeah. Okay. Fine. One more thing, which I can remark at this point is that if X has a norm on it, right, has a norm on it. So what do I mean by having a norm on it? So a more technical term would be that this topological vector space X is normable. That is, it has a metric. I am assuming it already has a metric. So this norm is compatible with that metric. That is, I can define that metric. I can induce that metric using this norm. So if X has a norm on it, then both of these notions will be the same. Then both deboundedness and usual boundedness are equivalent. While now we know that provided a metric, I can induce a different metric in this form, right? Okay. While if I consider this metric, which is still invariant, assuming D is invariant, obviously, because we are considering this to be a metric on a metrizable topological vector space, which is invariant, and as well, and also equivalent to D. What do I mean by equivalent to D? That both of them induce the same topology. But still, so what is the problem that occurs? D1 boundedness is not equivalent to, so but still D1 boundedness, let me write just this, is not equivalent to usual boundedness, right? So even if I have a metrizable or rather more specifically a normable topological vector space, then we can see that the that with respect to the usual induced metric, both of the definitions are equivalent. But once we just construct out a different metric which is still equivalent to the initial metric in this way, then again the equivalence fails, right? Now we can talk about some specific examples of boundedness or bounded sets to be specific, and we will come up with a very important example. Now recall, so I am once more writing out a theorem which we have already done in some previous lecture, that suppose V is a neighborhood of the origin in X. X is again a topological vector space. Then number one, that if I choose an unbounded sequence of scalars, if 0 less than R1 less than R2, so on and so forth, and Rn tends to infinity as n tends to infinity, then I can write x as the union of Rnv, n is equals to 1 to infinity. Then I have from here that every, in fact it actually follows from 1 itself, every compact subset of k is every compact subset k of x is bounded. Okay, you can somewhat think of it from 1 itself, you can think of it from 1 itself. We had given a proof of both of these statements. There was a third statement as well. I am not keeping it here because it is of no use at this point. What I meant to give this here is to specify this, that we already have constructed out an example of bounded sets in a topological vector space, and those are the compact subsets. One more example, one more serious example of bounded sets would be closures of bounded sets, right? We have seen this in some previous lecture, that if I take closures of bounded sets, then those are also bounded. So closures of bounded sets are bounded, right? One example which I am specifically focusing on is that, so let me just write it as a proposition. Let X be a topological vector space and Xn in X be a Cauchy sequence. We have introduced the notion of Cauchy sequence in the previous lecture. We have Cauchy sequence. Then this sequence Xn, you can some sort of treat it as a set of elements, regardless of repetition of elements in the sequence, but that's something else. That won't cause any problem to be very specific. But then Xn is bounded, and posteriori, that is once we prove this, all convergent sequences are bounded as well, right? Fine. So let's see the proof of it, and the proof is specifically very simple. We just abide by the simplest topological definition of Cauchiness. Okay. So as given, let Xn be a Cauchy sequence in X. Fine enough. Let me go to okay. Let me start the proof in a different page. Yeah. So proof. Let Xn in X be Cauchy. Now in some previous lecture we had also discussed about this, that we can obviously get hold of balanced neighborhoods around origin. So let V and W be balanced neighborhoods of the origin in X, such that they obey this property, V plus V is contained in W. Okay. Now from the now just look back to the usual topological definition of Cauchiness, that we say that a sequence is Cauchy if the usual definition if the usual difference of elements of the sequence eventually are contained in inside the members of a local base, right? So now from the usual definition, by usual definition I mean the topological definition of Cauchy sequences. So it must be in the neighborhoods around origin. The difference between them must be eventually in the neighborhoods of origin, and we already have chosen a neighborhood V of origin, right? So by the usual definition of Cauchiness, there exists some natural number n such that in fact we can remove this restriction that these indices come from the natural numbers, because when we are in a topological space, our usual generalization of sequences, which we call nets, are more prevalently used. So in fact rather than talking about some specific indexing set, which we in very usual sense we used to be the natural numbers, we can actually go for any arbitrary indexing set. Okay, any arbitrary indexing set having a partial order, and there are some certain more important properties which we require for that indexing set, which is not dedicated to the course, to the part of this lecture. But if you have studied nets, then you would know that what sort of properties do we require for an indexing set in order to define a net, right? It needs to have the direction property, and there are certain more properties as well. Okay, reflexive property is also one of the properties required. The most important property is being a directed property. Okay, that is provided you have two distinct elements. There exists a third element such that it's greater than or equal to both of these elements, some sort of like that. Whatever, we don't indulge into that sort of a concept. So now from the usual definition of Cauchy sequences, there exists some index n such that xn minus x capital N is contained in V, and which I can equivalently write like this. Fine, right? And this happens for all n greater than equal to n. Now choose a scalar s greater than 1 such that this xn is in SV. Okay, then what can I do typically from here is that then xn, which was already in x capital N plus V, so I can write this to be inside SV plus V, right? But then this would be contained in SV plus SV, and then this would be contained in SW, and this happens for all n greater than equal to capital N. Fine. But then this implies that xn is in TW for all n greater than equal to 1 for sufficiently large t, and which means that the Cauchy sequences are bounded. Fine. So we serve as a last sort of an example, and then we will be ending this lecture. Observe that, so this is not to be specific an example, but rather an observation. Suppose x is a non-zero element from a topological vector space capital X, and I define E to be this set Nx such that n comes from capital N. Then E is not bounded. Why is it so? As we can always find a neighborhood V of the origin such that x is not in V, right? For example, if this is my topological vector space, this is my origin, and suppose this is my x, so I can always get hold of a neighborhood which does not contain x. Okay, you can think of it in some sense to be the Hausdorff property. So this is in some sense, you can think of it in some sense as the Hausdorff property, not as strong as the Hausdorff property, but closely related to that. Whatever, not necessarily not to be discussed here at this moment, but yeah, we can do that obviously. But once we have this, then that means that Nx cannot be in NV, but that means that no NV. Now since all these are arbitrarily talking about, so no NV contains E. So by the usual definition of boundedness, E cannot be bounded. But what does it typically speaks as? So consequently, no subspace of X is bounded, or rather can be bounded, other than 0. Fine. Now so you need to emphasize on what I have here is a subspace and not a subset, right? And why is it true? You can some sort of think it in this way, because we have closures inside a set, inside a subspace. So if I have some number of, if I presume some number of elements inside that subspace, I can keep on adding them, and I can keep making the subspace large and large and large, so I can never confine it within some neighborhood, some scaled neighborhood, right? Yeah. Fine. So let this lecture be up till this much. In the next lecture we will talk about some characterization of boundedness in terms of sequences, and we will talk about bounded linear functions. So meet you guys in the next lecture.